Dear students, welcome back to our channel. Namaste. Today we are seeing the sixth problem from the 2024 year's paper of ISI MSTAT. This is a subjective problem and it goes like this. So assume that we have length in minutes of phone call of an individual that follows an exponential distribution with an unknown parameter lambda. So we are having phone calls. So the phone call length, as you all can understand, it will start at a certain point and it will go up till some value. So that value t is being modeled using an exponential distribution. Okay. So that has an unknown parameter that we call as the scale parameter of exponential distribution. So suppose it is lambda. However, when the phone company calculates the length, so basically they are doing an approximation because we can't always calculate things exactly, right? So suppose we have 22.09 minutes and the company actually notes it down as 23 minutes. So the question is that suppose we have data on a lengths of n independent phone calls. So we have phone calls, n many phone calls, they are independent observations. So they are random observations and they are as recorded by the phone company. Suppose we denote them using T1 up to Tn. So suppose we have this data. Based on this data, we have to calculate or compute the maximum likelihood estimator of lambda. So there is quite an interesting problem because we have the observations following exponential distribution. Then the company is recording it with a certain kind of approximation. And that value is also random. That will definitely depend on the actual phone call length. Based on that approximated value, we have to infer about lambda. So let us see how you can do that. So since we are approximating, we are actually taking the nearest integer greater than or equal to the actual length, right? So in terms of mathematical functions, to be precise, we're taking the ceiling value. So there are two kind of functions. One is called the floor function, and the other one is the ceiling function. So they have this kind of notations. So in one, we are actually taking the integer that is nearest to it, but less than equal to. In the other one, we're taking integer that is nearest but greater than. So that is the ceiling value and the floor value. Now we can actually denote it as the ceiling of x. So x is the actual random call length that follows the exponential distribution. Then t will be defined as the ceiling of x. Now the question arises, what kind of random variable is t? And we have to compute the MLE of lambda based on those random observations. Now to compute MLE or to maximize the likelihood, we need the likelihood. To, to calculate the likelihood, we have to know the distribution of t. So what is the distribution of? So finding the distribution of t is actually simple. If you think for any realization or any phone call length, t will be a positive integer, right? So for any non-negative random value of x, t, that is the ceiling of x, will be a positive valued integer. So the distribution of x must be discrete. It must be discrete. And it should take values 1, 2, 3 up to infinite. Now comes the calculation of PMF. Suppose t is any point. Probability t equal to small t means probability ceiling of x equals small t. Now that is probability x greater than t minus 1 less than equal to t, right? Because any value that lies that is strictly greater than t minus 1 and less than equal to t, everything will be approximated when we are taking the ceiling function to t, right? So if we calculate, this comes out as probability x less than equal to t minus probability x less than equal to t minus 1. Very simple. So once we are taking things common, we will end up with this kind of form. So q lambda power t minus 1 times p lambda, where p lambda is this quantity, 1 minus c power minus lambda. And this we are observing for t equal to 1, 2, and so on. So t follows a geometric distribution that we all can understand now because this is a PMF of a geometric distribution. So that is actually counting number of failures until the first success. So it is quite strange that this kind of analogy is coming, but the form is very interesting. And you can give it a thought that why this kind of analogy between exponential and geometric distribution is there. So yeah, you can think and maybe mention something in the comments. So this is a geometric distribution with this kind of a success probability. Now that means we will have a likelihood of n observations, right? So likelihood of lambda given observations small t1 to small tn, that is just the product of individual probabilities. And that will be product of n geometric observations or geometric probability values at n points, and this will take this kind of form. So to obtain the MLE, we will do a trick. Basically, as we all can see, that p lambda is 1 minus e power minus lambda. So e power minus lambda is 1 minus p lambda. So this will be 1 minus p lambda power sum of ti minus 1. So this will be the likelihood function, the joint likelihood function, and we will actually find out the MLE of p lambda. Then we will use invariance property of MLEs. This will be a simpler solution. Instead of just maximizing it with respect to lambda, we can do that directly first using p lambda. So if you take derivative with respect to p lambda and put it equal to 0, you will obtain the MLE of p lambda as n by summation ti. That is the inverse of the arithmetic mean of ti observations. Now that is the MLE of p lambda, but we need MLE of lambda. So by invariance property, we are obtaining this. So if we put the MLE inside the function p, or rather if we just calculate the MLE of the function p lambda, they are the same by definition. So we are actually obtaining this first. So this is being put over here. Now p of lambda MLE, that is 1 minus e power minus lambda cap MLE. So upon simplification, this is the form, and this is the simplified form. Okay. So this will be the answer. And actually we can further explore that suppose we have this kind of an estimator. Now the question may arise that, okay, we are approximating the phone calls. So wouldn't it affect the inference about lambda? By this I mean, would it not change the values of lambda once we are actually estimating? It will be what kind of an estimator? Will it be a good estimator? Will it be an unbiased estimator? What will be the variance? Is the variance less than the original? Obviously, that will not be true, right? Because geometric distribution, it comes under the exponential family. So the UMV will be the sample mean. And it is not true in general. Well, there is another catch over here, that what is the like the mean. The mean is, it will depend inversely upon p, right? The larger the value of p, the smaller the realization. We will achieve success faster. So it is inversely proportional to p. So the UMV of 1 by p can be obtained, and in other ways we can obtain the UMV of p also using, I think, Rao Blackwellization. We can actually obtain that. But the question comes, that estimator and this estimator are the same? Are they different? What is the difference in between their variance? So these things you all can explore later also, maybe in some blog or whatever, we can put those things. So yes, this is all about this video. Thank you again. Hope you will watch other videos as well. We are trying to upload the solutions of 2024 year's exam of ISI MSTAT, and I hope you all are liking this series. If you like, please do consider sharing with your friends, those who are aspiring, your juniors, and anyone you like. Till then, bye, take care, and Hare Krishna.